In question 4, we're told experiments on the photoelectric effect, where light is shone on a metal surface, demonstrate the particle nature of light. In A part 1, we need to state what is meant by the threshold frequency of the light. Well, the threshold frequency is the lowest frequency at which electrons will be emitted. In part 2, we need to explain why the effect is not observed below the threshold frequency. Well, the energy of a photon of light depends on the frequency, and below the threshold frequency, the photons have insufficient energy to release an electron. In B, we have monochromatic light with wavelength 5.40 times 10 to the minus 7 meters, landing on a metal surface with a work function of 1.40 times 10 to the minus 19 joules. In part 1, we need to calculate the energy of a single photon of the light. Well, from the formula sheet, photon energy E is equal to Planck constant h multiplied by the speed of light in a vacuum c divided by the wavelength. Putting in the values, the Planck constant and the speed of light are given on the formula sheet. The wavelength from the question gives a photon energy of 3.68 times 10 to the minus 19 joules. In part 2, we need to calculate the maximum kinetic energy of an electron emitted from the surface. Well, for this we can use this equation. The maximum kinetic energy of the electron is equal to hf, the Planck constant multiplied by the frequency, or the photon energy, which we've found here, minus the work function phi. Putting in the values, this is the photon energy found previously, this is the work function given in the question, gives a maximum kinetic energy of 2.28 times 10 to the minus 19 joules. In part 3, we need to calculate the maximum speed of these electrons. Well, for this we can use the kinetic energy is equal to half mass times speed squared. Rearranging for the speed, we get the speed is equal to the square root of 2 times the kinetic energy over the mass. Putting in the values, this is the kinetic energy found in part 2. The mass of the electron given on the formula sheet gives a maximum speed of 7.1 times 10 to the 5 meters per second. And finally, in part 4, we're asked to calculate the de Broglie wavelength of these electrons. Well, de Broglie wavelength is equal to the Planck constant divided by the momentum, or the mass times velocity. Putting in the values, the mass of the electron, the velocity found in part 3, and the Planck constant, gives a de Broglie wavelength of 1.03 times 10 to the minus 9 meters.